I'll be back. All right, great. So let's start off. So we're gonna have our next talk is gonna be by Hoeteck, who's gonna tell us about GGH15, which is this really great approach for building I/O and much more. That's been around for 10 years, and we're still trying to understand it.
All right, so I changed the title of my talk. I wanted to mirror the title of the program down to the Oxford comma. So I'm going to be talking about GGH15, 10 years later, obfuscation, witness encryption, and invisible WE. So let me start with a quick recap of the definition of I/O. It's the same one that Rachel used in the talk. So an obfuscation algorithm takes input circuits, produces obfuscated circuits that should have the same input-output behavior as the original circuit. And the security requirement is that for given any two circuits with the same input-output behavior, namely they agree on all inputs, the obfuscation of the two circuits C and C prime should be computationally indistinguishable. All right, in this talk, we'll also be looking at the relaxation of I/O, namely that of now I/O, where the correctness requirement is exactly the same as before. So you can obfuscate any circuits and should preserve functionality, but the security requirement is weaker. Namely that we only require security for now programs. Now programs are programs that output reject on all possible inputs. So for now programs, the obfuscated program should be indistinguishable. And again, correctness should hold for all programs. And why do we care about now programs? One reason is that it implies witness encryption. This is a very powerful form of public key encryption, where the public key is any MP statement, and you can use any witness for the statement as a secret key. All right. So in this talk, I want to revisit a beautiful paradigm for building I/O based on the so-called GGH15 encodings. This was introduced in the work of Gentry, Gorbunov, and Halavi about 10 years ago in the context of multilinear encodings. And I'm going to be describing the construction and looking at it, and I'll be adopting essentially some of the simplifications from the work with Ilian and Vinod. So let me jump right in and tell you how this I/O for via GGH15 encodings work. All right, so the input to the program in this case will be represented as a branching program. So for this talk, I think our branching program is being specified by a vector U, which is a 0-1 vector, and a collection of matrices, square matrices with 0-1 entries. So you have many pairs of matrices. And on an input of length L, the program accepts if we take the subset product of these matrices as indexed by the input X and multiply by the vector U on the left, we get the all zeros vector. If we get the all zeros vector, we accept, otherwise reject. So as written, this is the definition for read-once branching programs. So the length of the input and the number of matrices are exactly the same. But the definition also works for read-many branching programs. So for this talk, I'm going to only focus on read-once branching programs. But let me just say that essentially all the results here extend to the read-many setting. But essentially, you can transform any read-once branching program into a read-many branching program. Sorry, you can transform any read-many branching program to a read-once branching program at the cost of blowing up the length of the input by just repeating your inputs many times. And in this read-once program, you would need to check that the input is well-formed, so it's well repeated. And if so, you run the original program. Otherwise, there should be additional consistency check that rejects. And for the purpose of this talk, it's useful that this consistency check can also be computed by a read-once branching program. So anyway, for the rest of this talk, I'm only going to focus on read-once branching programs. All right, so let me tell you how the construction works. It's actually extremely simple. Let me first say the high-level approach. It's sort of related to the paradigm introduced in the earlier work of Gard et al., where basically, essentially, given a branching program, we're going to encode the branching program as follows. For the vector U, we're going to encode it as a matrix C0, and each of the M matrices, we're going to encode it into a matrix D. The output of the obfuscated program is going to be C0 together with the encoded matrices, DIJs, DIBs, I guess. And to evaluate the program, we're going to essentially take a subset product of the D matrices, multiply by the C0 matrix, and check whether it's small. So these matrices we're going to get are going to be, the entries are going to come from some large integer modulus Q. So we're going to check whether when you multiply them, it's going to be the entries are all small. If it's all small, then we're going to accept, otherwise we're going to reject. Okay, this is basically the basic paradigm. And it's very much related to the idea of doing multilinear encodings and zero testing. So checking whether something is close to zero essentially corresponds to what we call zero testing. Okay. So this is basically the basic template. And really, the interesting part is how do we compute the encoding C0 and the D matrices. All right? So the encoding is going to proceed in 3 steps. The first step is to do a Killian-style randomization. So we're going to pick matrices A0, A1 up to AL minus 1, 1 for every bit of the input. But instead of picking square matrices, random invertible square matrices like in Killian, we're going to pick in white matrices. All right. Think of these matrices as corresponds to the white matrices in your LW assumption. So this is going to be assumption matrices where the entries come from ZQ, where Q is some large modulus. And then now, when you have a white matrix, multiplication by AI is still well defined. AI inverse is a bit trickier to define. It's no longer the way the matrix inverse, but rather AI inverse is going to sample a Gaussian pre-image of whatever the input is. Okay? So in particular, AI inverse of P will be a matrix D such that AI times D is equal to P. And D is going to have low norm, the distribution will be Gaussian. For the purpose of this talk, the detail of Gaussian isn't so important, but that's basically roughly speaking how we define AI inverse. Okay? And now if you multiply everything together, you get UMX as before, multiplied by the last matrix AI on the right. Okay? So this is going to be 0 if and only if UMX is 0. All right. So far, so good.
If you have the stronger Barrington-style notion of branching program without the U, where the MX directly corresponds to the output of the function, does this simplify anything?
With MS,
The U is kind of helpful for efficiency purposes. But
yeah, I think it's useful to think about the whole thing as a vector. For instance, it allows you to directly encode MP statements as a weak-branch branching program. Okay, so this is the construction so far. This is the first step. Next, we're going to essentially add noise to each of the inputs to the A0 inverses. All right? What this allows you to do is basically to argue by the LW assumption that if you look at the marginal distribution of any pair of encodings for the fixed input bits, they're going to be pseudo-random. Right? This is very different from Killian randomization, where you are only allowed to look at one of the 2 encodings per input bit, otherwise security is lost. Here, we can use a combination assumption to ensure that the marginal distribution of every pair of encodings is pseudo-random. Right? And here we use the fact that there's a noise. And this essentially follows from the LW assumption, where the reduction essentially treats AI minus 1 as LW secret. And then the noise that you add, which I denote by a straight green line, corresponds to the error in the LWE assumption. Okay, so this is good. And now there's one more step. We need to perform some additional randomization to essentially prevent attacks where the adversary tries to cancel out the AIs. And here, we need to introduce additional randomization, where we replace each of the matrix M by MI tensor SIB, where SIB is a random low norm square matrix. So if you're not too familiar with the tensor product, just think of this as multiplying by random scalars. And the tensor product with square matrices is the correct higher dimensional analog of multiplying by scalars. It has all the nice properties like things commute and so on and so forth. But the one dimension already makes sense if you're, for instance, willing to work with ring LWE. Okay. So,
the purpose of this?
I'm sorry?
Why are you doing this last step?
Good. This will allow us to sort of avoid attacks that try to cancel out the A's. In particular, it's going to be the case that when you multiply everything out, you get different things multiplied by the ALs. And if you don't have additional randomization terms, you can, if you get all of the computation multiplied by the same ALs, you can actually learn something about this UMX beyond just whether they're 0 or non-zero. Okay, this tensoring by random secrets also actually prevent mix and match attacks. So this is sort of the entire construction. That's it. So you do Killian-style randomization, add noise, and tensor by random secrets. That's all. All right. So this is and then you can check that when you multiply everything together, this is what you get. And correctness basically follows from the fact that if UMX is 0, this is going to be a small value. If UMX is non-zero, this is going to be essentially a large random value. So you're not going to get something close to 0. Okay. And the nice thing about this construction is it's extremely simple. All right? And in fact, it's even implementable. And there's a work of Halevi, Noah, and Victor Shoup that actually implemented some variant of this thing. Right? It takes a lot of memory, and you can only obfuscate very, very small programs, but it's still potentially implementable. Okay, so given that we have such a simple construction, a very natural question is what can we say about it? Right? And remarkably, this construction is not only simple and implementable, but surprisingly robust. Okay? We can think of it as an I/O candidate. Turns out there's an attack, but there's also a very simple fix. And with the simple fix, there's been no attack so far. As a now I/O candidate, there's no known attacks for the construction S's. So given that we're such a beautiful and simple construction that people tried to break and couldn't break, we'd like to say something about it.
Can you relate this to the original I/O construction of Garget al? Like in what way it simplifies the multilinear map-based construction?
Right, so if you implement the multilinear maps with GGH15, it's basically the construction you get. Yeah, sort of. I find this slightly easier to think about because you don't have to think about the Killian-style randomization and the sort of directly go into the encoding. Then you don't have to think about straddling sets and stuff like that. So again, as a now I/O candidate, as this there are no known attacks. In fact, we have some security proofs. All right? For special cases of the now program, we can prove security of the scheme from the LW assumption. Okay? And in a more general setting, we can actually prove security from what we call the evasive LW assumption. This is a new assumption that was invented partly to prove security of the scheme, but it's a bit more than that. All right? So for this talk, I'm going to tell you a little bit about everything. So I'm going to start by telling you how to prove special cases of this construction for special cases of null programs from the LW assumption. Then we'll tell you about the attack and the fix, and then I'll describe the security proofs for the general now I/O setting from the evasive LW assumption. Any questions, especially about the construction? Okay, good. So now all special cases. So the first program, the first special case we'll look at, and basically almost the only one we'll look at, is the case of permutation programs. So each of the matrix MIB is going to be a permutation matrix. In particular, if you take any subset product of the matrix, it's also going to be a permutation matrix. So it's going to be non-zero. So this corresponds to the null program. Right? Just assume that U is a non-zero vector. Okay. And for this specific class of null programs, we can prove security of the scheme from the LW assumption. Right? And this very simple construction for the very simple class of null program already has applications towards constructing private constraint PRFs for OP and C1 and lockable obfuscation. Okay. And this particular result that we'll describe was sort of following the work of Kennedy Chen, but also independently proved in the work of Rishabh and friends and Danny and friends. All right, so I'm going to I'm going to do the proof for the special case where the program has length 2. Okay, the proof scales to numbers larger than 2. And what we roughly want to show is that these encodings hide the matrices MIBs. Okay. In fact, we're going to show that something stronger is true. We're going to show that it hides the MIBs even if you're given the intermediate matrices A1 and A2. Right? So given A0, A1, and A2, all the encodings look pseudo-random. The security proof follows what we call the right to left strategy. So we're going to start by looking at the encoding on the right and start moving all the way to the left. Okay. So let's focus on the terms that are on the right-hand side. So the ones that involve A2. Right. Here, it turns out that if M's are permutation branching programs, you can basically show under the LW assumption that these quantities are pseudo-random, where A2 is your public matrix and the S are your LW secrets. Okay. Your permutation branching programs basically permutes LW samples. Okay. So the permuted LW sample is still pseudo-random. All right. So you can replace all of this with random, so uniformly random ZQ elements. Now let's peel off one more layer to look at what happens when we put A1 in. Now, A1 of uniformly random matrices are going to be uniformly random Gaussians. Right? So you can replace this with random. So now you have gotten rid of the A1 inverse, which requires computing with a trapdoor for A1. So now you can move one level back. And again, you can now do LWE with respect to with the S matrices, your secret, and A as your public matrices. Replace this with random, and then replace everything with random. Right? That's the entire proof. Questions? Okay, we end up finishing early, but good. All right, so this works for permutation branching programs, and this is one specific class of null programs. And in fact, in follow-up work, we showed that we give an extension showing that the construction is secure for a slightly larger class of null programs. All right? These are programs where they are no longer structured like a permutation program. Rather, your U matrix has a 1 at the corner, and your M matrix has a 1 at the bottom right. Okay? And then these are zeros. Everything else can be arbitrary. And it's easy to see that this is, again, a null program, because when you multiply everything together, you get a row vector where the last entry is always 1. Okay? And for this particular class of null programs, we can also prove security under the LW assumption. It's independently done in the work with Elaine and Vinod, and also independently in the work of Rachel et al. All right, so I'm not going to do the proof for this statement. Rather, I'm going to go to the next part of the talk, namely the attack on I/O and the fix.
Hoeteck?
Yeah.
How do you implement constraint PRFs using null obfuscation?
How do you present a constraint PRF using null obfuscation?
The techniques are the same, but it's like I'm not sure if null obfuscation implies.
Right. So we're not going to generically implement constructing private constraint PRF from null.io. Rather, we're going to use this particular construction to implement the constraint
The
PRF.
techniques work, but there's no direct implication from null.io to constraint PRFs.
No, not generic construction, right? Rather, with this particular construction, once you prove security of this thing, this particular construction can be used to give you a null.io. Yeah. I think the M programs compute the constraint, and then this is the constraint key for the program. The PRF is sort of this BLMR PRF.
So the part that you proved, does it have like an application? Well, I know it's related to null.io and PRFs, but like, can you have an application just with
For this one?
either one, this one or the one before?
This one, yeah, it has. The previous one has applications to constraint PRFs and to lockable obfuscation.
And it's
In fact, you prove it.
it's related, but like the part that you proved directly, can you like, does that right away give null.io? Would you?
Does it give all the way to null.io? Wait, sorry. So this gives you a lockable obfuscation, and this gives you null.io for specific class of program. It doesn't give you null.io for the general programs.
But even lockable obfuscation, you have to do a little more. Like, for example, in your application, you have no way of telling if the output is 0 or not.
Right. You have to do a bit more, but the core part of the proof is proving a statement of this kind.
I guess I was asking if like just what you proved if it has an application, like just this.
I see. I guess not directly, but this is the core technical lemma in all of this.
Yeah, exactly.
You have to do a bit more work to upgrade it to do a bit more work, but this is the core technical lemma, and this is the core security proof.
I mean, one way to, you're saying, look at it is just that the proof of constraint PRFs and lockable obfuscation, the similar part is this part. In constraint PRFs, you have to use BLMR on top of it.
Yes.
Lockable obfuscation, you have to use kind of like the homomorphism and sort of addition.
Yes. You do something, but the core part is this statement. Yeah. Right. You have to do extra work to get to these things, but the interesting technical point sometimes is this, and this also gives you the construction. Yeah. Any questions? Right. So similarly, the applications for obfuscation in this sort of program is that you get applications for before where you can directly work with non-permutation branching programs, which gives you some efficiency. And this was, we did it in the context of trying to understand non-permutation branching programs. The other work did it in the context of constructing tracer tracing schemes. And then they were obfuscating the greater than or equal to program. Okay, good. So now I'm going to talk about what happens as an I/O, the construction as an I/O. I'm going to show you that there's in fact an attack. All right. In fact, there's an attack even if you're just using the construction to obfuscate weak branch branching programs. Okay. Now I'm going to tell you first the high-level strategy of the attack on I/O. So now to break I/O is sort of a bit inconvenient because I need to first construct a pair of programs, show that they're computationally that they are functionally equivalent, and then yada yada yada. Right? Instead, I'm not going to not quite do that. I'm going to essentially tell you. I'm going to give you a program with certain properties. I'm going to show you how to learn certain non-trivial amount of information about the program, which intuitively you should be able to learn. Okay? To turn it into a full-fledged I/O attack, you have to construct a pair of programs with all of the right properties. But that can be done. All right, let me start with the high-level overview of the construction of the attack. What you do is, well, first of all, we must crucially, we say that there's no attack on I/O. So any attack here must be on I/O. So it must crucially use the fact that you have accepting inputs. So the construction looks at the program, and looks for L squared accepting inputs. L is a parameter that, roughly speaking, grows with the width of the branching program multiplied by security parameter. Accepting inputs of the following form. Okay, it's essentially what in complexity theory they call a combinatorial rectangle. What does that mean? I'm going to look at inputs of the form. So I'm going to pick L inputs of length L over 2, capital L inputs of length L over 2, and then another L inputs of length L over 2. So these are the Y1s up to YL and Z1 to ZL. I'm going to consider all L squared inputs that you get from just concatenating all pairs of these inputs. Okay. So this gives you L squared inputs. All right. And then I'm going to essentially run, the idea is that I'm going to learn the rank of the following matrix. These are the matrices that you get when you essentially do a partial computation of the branching program on the first L over 2 bits of the input. All right. So what this quantity essentially says is that you learn something about the internal state of the program after you read the first half of the input bits. All right, this is something you shouldn't be able to do if the program, if you have I/O which hides all internal workings for the programs. All right, this is the high-level strategy. All right. Any questions? Okay.
Yeah. What is it supposed to teach us?
I'm sorry?
The rank. What is the rank supposed to teach us?
Good, good. Yeah, it tells you something about the internal state of the program. Sort of, if you pick this thing correctly, it sort of tells you whether the overall of these inputs are spread out across many different states, or sort of compressed and sitting on sort of concentrated on some small number of states.
But does rank capture everything? Like, can't you get some more spectral information beyond rank?
Capture everything in terms of capture all known attacks, or
Yeah. My question is whether you cannot generalize the knowledge of the rank to knowledge of more spectral information, like eigenvalues.
I see. Good. So I think the rank is a particularly easier one to work with. Some of the earlier text talks about some sort of eigenvalues, but turn out you can just look at the rank. And it'll be, once I describe the attack, it'll be a bit clearer why the rank is particularly relevant. But if you can learn the rank, you already learn non-trivial amount of information. Good. So the construction, the attack sort of follows what's called the zeroizing attack framework, which was introduced in the context of multilinear maps. So roughly speaking, what I'm going to do is I'm going to evaluate the program on these inputs. All right, what does it mean to evaluate the program on these inputs? I'm going to take a subset product of the encodings, right, and then multiply the C0 matrix. And since these are accepting inputs, when I take the subset product of the encodings, it's going to produce a small value. All right? So the small value mod Q in particular will give you a quantity that's over the integers. And the good thing about over the integers is that you can start doing, Gaussian elimination and all sorts of crazy linear algebra that may not make sense in the mod Q setting. Okay. So I'm going to compute. The program on this L squared input, so I get this L squared encodings. I'm going to take all of these values that I get, which is a matrix Wij for each of the L squared inputs, and arrange it into a big square matrix. Okay, where the ith block of the matrix is the evaluation on the x, y, I, z shape. Right, so I'm going to arrange this whole thing into square, and then the attack essentially just outputs the rank of this matrix. Okay? And the claim is that the rank of this matrix is related to the rank of the matrix that I described earlier. All right, so you evaluate your program on L squared inputs, you arrange them in the square the same way you arrange your inputs into square, and then you just output the rank. All right. So let's see what happens in the construct. Let's try to analyze why the rank of W leaks information about the program. All right. So remember, we'll assume that the program is read once. So when you talk about the subset product of the encodings, it's going to be a subset product of two encodings, one that only depends on the Ys, and the other part is going to depend on the Zs. That's why we use the fact that we take inputs that form a combinatorial rectangle. Okay. And this means that the W here also decomposes into a product of two matrices. All right? The first half depends only on the Yi's, and the second part only depends on the Zj's. Okay? And the point here is that the width of these matrices are more or less fixed. They depend only on the width of the branching program, whereas the height, you can just sort of pick arbitrarily large. You can make that height arbitrarily large by picking your sufficiently many inputs. Okay, so now it turns out that these matrices Y and Z are going to be low norm. So this is sort of a equation over the integers. Moreover, heuristically, the matrix Z is going to have full rank. So this means that the rank of W is the rank of Y. All right. Now, what's the rank of Y? If you look at what Y looks like, it's going to essentially encode information about the partial product so far, together with tensor with some subset product of the S matrices, together with some error terms. All right. And again, making some heuristic assumptions. So, by the way, all these attacks on I/O are sort of heuristics. You assume that Gaussians behave somewhat independently, and then you verify these heuristics by writing a computer program. Good. So turns out, assuming standard heuristics, the rank of this matrix is essentially only going to depend on the rank of this matrix. Okay, and therefore the rank of W is essentially going to be rank of Y multiplied by some security parameter, which is fixed and independent of the program. All right, so you learn this, which leaks information about intermediate state of the programs, and therefore you learn something about the program. All right, that's sort of the entire attack. Any questions? So the rank is sort of particularly suited because you really use the fact that you can pick many more inputs than the size of the program, and then you get this decomposition property. Yeah.
Where did you use the fact that it was an I/O and not a null I/O again?
Good. We use the fact that it's an I/O because you use the fact that these values are all small, and then you get small values, and these are equation over the integers. And the rank here actually refers to, for instance, the heuristic. All these heuristics about full rank and blah 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 are all sort of about Gaussians over the integers and not about mock Q objects.
How do you argue that Z is full rank?
How do you argue that Z is full rank? That is a heuristic. You sort of assume that. So we know what we can show is that Gaussian pre-images are full rank. That's more or less standard. And then these are actually subset product of Gaussian matrices, so it's a bit harder to analyze. But yeah, in the attack world, most stuff are heuristic. I think it's not uncommon to. You have to write a program to verify that it works. Yeah, somewhere on GitHub or Eli's GitHub. Okay, any questions? All right. Good. So how can we work around these attacks? One is just to make sure that we avoid encoding of zeros. So this we crucially use the fact that you get small values, so that mock Q and over the integers are the same thing. All right, and you can avoid encoding of zeros by making sure that the program never outputs zeros, which corresponds to obfuscating now I/O. Okay. The other is to sort of move to the read many setting. I know I said that we don't really think about read many programs, but you can still think about read many programs. And here, for read many programs, you can show that the attack grows. If you read C, the complexity of the attack grows exponentially in C. Okay? In particular, if C is very large, like lambda, the attack no longer works. So what you can do to avoid the attacks is just artificially pad your program to be read lambda. Okay, just essentially by padding your program with the identity matrices. All right? And that gives you an I/O candidate that is not broken, and for which we have no attacks. All right? This may seem a little bit ad hoc, but in work with Ile, Vino, and Minky, we showed that these attacks are related to what we call matrix PRFs. So whether you can compute a pseudo-random function using read-once branching programs. All right? And there, basically, you can use the same attack to show that you cannot compute a pseudo-random function using a read-C branching program for any constant C. But then when C is something like lambda, we actually have heuristic matrix PRFs that are not broken. So this sort of ties into this, gives some explanation for why this read lambda padding workaround actually may be buying you something. Right? Okay, so that's sort of the state of the art for I/O. Unfortunately, we can't prove too much more. Let me just go back to the setting of I/O and show a security proof of I/O under some reasonable assumptions. Concretely, we're going to be proving security of the construction under this evasive algebraic assumption. All right, let me say what the evasive LW assumption is. Fixed sum distribution S and P. All right, S is over very tall matrices, and P is over very wide matrices. All right. The evasive LW assumption is sort of a souped-up version of LW assumption. We want to understand the following question. All right. Given LW is sample SB plus E, together with some Gaussian preimages with respect to this matrix P, can we show that is SB plus E pseudo-random? All right. In general, this statement is false. If P is a gadget matrix, B inverse of P leaks a trapdoor for B, so all hope is lost. But we can still hope that maybe for some matrices P, SB plus E is still pseudo-random. All right. First, let's see what are the attacks that you can have given these quantities. All right. What you can definitely do is to multiply your LWE sample with the Gaussian preimage to get an LWE sample for SP plus E prime. Okay, this is something you can do. And the claim is that if this LWE sample is also pseudo-random, then basically that these are the only attacks. Right? So if this is pseudo-random, then there are no other attacks. All right. So this is basically what the assumption says. I do want to emphasize two things. One is that the attack sort of assumes, intuitively the attack says that all attacks must work by multiplying these two quantities together. Right? So it has a flavor similar to, let's say, GGM for bilinear groups that says that the only thing you can do given elements in G1 and G2 is to pair them, move them to GT, and then try to do something. Okay. There's one additional subtlety here, namely that when we give out this new LWE sample SP plus E prime, we're putting in a fresh error rather than the structured error you get from multiplying these two terms together. All right? So one way to think about it is that if the most significant bits of SP is pseudo-random, then basically, SP plus E is pseudo-random. Okay? And in particular, this sort of this precondition basically avoids the zeroizing attacks, which corresponds to setting where when you multiply these two together, you get a small value, in particular, which are not pseudo-random. Okay. So that's sort of the evasive LW assumption. So one simple example is when S and P are both the uniform distribution, then you can prove both the pre and the post condition from the LW assumption. This is sort of a little bit too simple. For applications, the distribution are a bit more complicated, namely that you want to allow both in this pre-condition and the post-condition some auxiliary input that depends on the matrices S and P. All right. In fact, this in general will be some sort of private coin auxiliary inputs. And this is where the trouble kicks in. In fact, the assumption is false in the most general setting. So you can sort of embed an obfuscated program into the auxiliary input and embed some sort of a trapdoor for P into the program. And then you can sort of distinguish between these two distributions. Or it allows you to check whether SP plus E is the product of two small things. All right. So to work around this, well, we can think of the obfuscation-based counterexample as sort of what's the word? Never mind. Right, some unusual example, and then we can think that for natural settings, these things don't come up. In the paper, we also describe a particular class of auxiliary inputs correspond to some sort of private encoding of public values for which the obfuscation-based counterexample doesn't seem to apply. Right. So that sort of solves the problem, except more recently we have two attacks, very natural attacks, sort of just algebra, that breaks the assumption. Right. The first one basically uses the fact that given B inverse of P, and if you carefully choose your auxiliary input, you can recover B. All right. This is the work of Brusker et al. And this one turns out we can get around it by essentially adding an extra noise term to the P term over here. Right? And this noise term already exists in our construction anyway. Right? And here, this fix actually provably gets around this attack because you can show again from the LW assumption that B inverse of P plus E prime is pseudo-random. Right? So in particular, it will hide B. All right. The other attack is one from the work of Nico and friends, where the auxiliary input is SP mod Q mod 2. Okay. Here, you can also get around this issue by requiring that the auxiliary input be local. So your auxiliary input can, so there are basically two samplers, one that samples the S and one that samples the P, and you are and then you're allowed to have auxiliary input that depend on S and auxiliary input that depend on P, but not auxiliary inputs that depend on S and P. Okay, and this also gets around the counterexample. While making sure that the security proof still goes through. All right, so our security proof from before goes through unchanged, and these are already properties that are part of the original GGH15 encodings. All right. Let me also add that there's a different variant of the evasive RWA assumption that was introduced in the context of attribute-based encryption, and it's similar and different at the same time. The main differences over there is that the B matrix is public and the S matrix is random and secret. All right? And the auxiliary input is independent of S and public coin, so you actually don't have any of these attacks. Okay? And you will hear a little bit more about this in David's talk. Not quite, but somewhat. Right. So now let's prove security of our now IO construction from the evasive RWA assumption. Right? This is work with Vinod and Daniel. Let me say that there's a concurrent work of Rotem Saburi that also constructs witness encryption from the evasive RWA assumption, but for a much more complicated construction. Okay, well, if we prove security of the original GGH15 encodings. All right. We also prove NIO, whereas the concurrent work only proves witness encryption. So roughly what we want to show is that if this is an null program, which means that U times the subset product of the M matrices is non-zero for all X, then this encoding has pseudo-random under the evasive RWA assumption. Okay, again, by pseudo-random, I mean this is a random matrix and these are random Gaussians. All right. So how do we prove a statement like this? Good. So as a mental experiment, let's first think about what happens when we multiply all of the encodings together. So we consider all possible subset product of the encodings over all possible inputs. So there are 2 to the L possible subset products. All right? And we consider these encodings with 2 to the L independent error terms. Okay? Let's first try to show that this distribution is pseudo-random. Okay? And turns out it's not hard to see that this is, again, from our correctness analysis, is exactly this expression over here, which decomposes into a product that is a non-zero vector multiplied by a PRF. Okay? And this is exactly the PRF, and this is pseudo-random. This is non-zero, so this is also pseudo-random. All right, so the 2 to the L evaluations are pseudo-random. Let's now look at what happens if you go one step back. Okay? So consider all possible 2 to the L minus 1 evaluations for all inputs of length L minus 1 for the first L minus 1 bits of the inputs, together with the last 2 encodings. Now we want to show that this distribution is pseudo-random. All right? I'm going to show this essentially by using the evasive RWA assumption, by observing that this quantity are essentially of the something multiplied by A sub L minus 1. This are Gaussian pre-images of AL minus 1. So you can apply the evasive RWA assumption with the matrix AL minus 1. And basically, the precondition corresponds to what we already proved in the previous bullet. And then by the evasive RWA assumption, this is also going to be pseudo-random. Okay? And then you just keep peeling back, iterating this argument L minus 1 times, and you get that this thing is going to be pseudo-random. Right, so you're going to be able to replace C0 with a random value. All right. Now you still have these Ds, which could potentially steal the information of the M's, but here, basically, you can apply the essentially the same argument as before that I mentioned, where you basically treat A0 as your RWA secret, and then you can hide your encodings for the I equals to 1, and then then you can treat A1 as your RWA secret to hide the encodings for I equals to 2, and so on and so forth. You can prove that everything is pseudo-random. This is sort of the left to right strategy. All right, that's sort of all that I wanted to say. So to conclude, today we revisited the I/O construction based on GGH15 encodings. I think there's still many more. There's still a lot that we don't understand about this construction. Right? So there's still more cryptanalysis work to be done, both in the evasive RWA assumption setting, or that NIO candidate directly, or even the I/O candidate. Or can we do more proofs can we prove more special cases of NIO from the LW assumption? So here we only know how to prove it for very simple programs, for which in some sense we know why the program is false, correspond to all rejects, and maybe we can try to prove now programs that PV equivalent to the all reject program. And then that's sort of, to understand what PV equivalent is, you have to come for the talks later in the workshop. Finally, sort of mirroring the line of work from on ABE from E raised to LWE, can we prove security of the schemes from falsifiable assumptions? So really revisit the proof and try to understand, state proper falsifiable assumptions for which, for instance, we can prove now IO security. That will get around all these issues with the attacks. All right, thank you. Yeah.
So thank you for your presentation. So, do you have any uniform view of the recent attacks against events community? Because I think many attacks use this similar different approaches. So, do you have any idea to unify these attacks?
Oh, I see. The question is, is there a way to unify the attacks on events LWE? That's a good question. So first of all, I think it's important to realize that by now there are many different variants of events LWE. So I described sort of two classes on this one, and then there are this circular events of LWE that looks very different, and the attacks are also very different. So given that the assumptions are somewhat different, it may be a bit hard to try to find a general theme to these attacks. I think it would definitely be nice to unify the attacks, then it gives you a way to better defend against these attacks. But up to now, the attack seems to, I think what's nice is that each of these attacks works for different reasons. So in some sense, what you don't want to do is to propose an assumption that got broken by known attacks. Right? That's sort of like you didn't do due diligence. Whereas if you have an assumption that's broken by new attacks, then in some sense, A, you are making progress on cryptanalysis. People are inventing new attack techniques. And B, if you have a fix around the attack, in particular, if the attack breaks the assumption that doesn't break the scheme, it gives you new insights into why the scheme wasn't broken, in some sense. And then you can try to come up with a new assumption that sort of captures the scheme but avoids the attack, which is what we do. I want to, so this is sort of a good thing. So these attacks are really working for fundamentally different, very different reasons. So in that sense, it's very nice. And I want to sort of emphasize that this is not like the case of, like this mouse and cat games who are running around in circles. I really do think that here, for GGH15 encoding, it's particularly valuable to have all of this, to do all of this because the construction is extremely simple and people really try to break it. So the fact that it hasn't been broken suggests that there's some new source of hardness that we don't understand. So that makes this exercise, in some sense, a bit more meaningful.
So relating maybe a bit to Paul's talk yesterday, if you apply this scheme to a fuzzy point function, a random fuzzy point function.
So apply to?
A humming ball, like a random humming ball.
Okay.
Okay, again, it's not meaningful as I/O, but let's make leap of faith that it will act as ideal obfuscation. So now the question of game-based security becomes really kind of a simple question. Can you hope to prove security? So again, security of recovering one-wayness, right? So you have a humming ball with a secret center. You apply, it has a very simple and natural branching program. You apply this construction. Can you find the center of the humming ball?
Yeah, that's a great question. Even for like point functions, we don't really know how to prove anything. So.
Okay, but now it's a very falsifiable assumption, right? That it's secure for point functions.
Right, I agree.
Okay, but what's the simplest form of this assumption? So that's a great research question. Is this construction one way when hiding a point function? Now can you simplify the assumption? Okay, can you make it into a self-contained simple question?
Right, yeah. Good. So I don't know the answer to the question, but let me first say that in what ways, so the question, how do you specify a simple assumption to reason about all these things? But there's also the question of what is simple. So
I mean, something that cryptanalysts will want to look at, right? So if you say, hey, I obfuscate, I mean, a point function is a bit less motivated from an application perspective, but the humming ball is already probably has tons of applications, and we don't have practical construction. So this seems very branching program friendly, okay? So first of all, figure out, okay, what's the concrete efficiency of that? If it's reasonably efficient, try to simplify the construction for this case, and then cryptanalysts will look at it. Right? At this point, they will not. They haven't. Right? So
right. Okay, so yes, so great. So we can take that as a research question. I think that's a good point, which is related also to the question of trying to prove now all security for simple classes of programs that you can directly reason about. Evgeny, you have a question?
Yeah, and I guess I know it's not the focus of the talk, but I mean, a priori, it's like at least for non-experts, if you say obfuscating null program is kind of, I mean, if you know the program is null, just, output the null program, right? So I would imagine the applications would be that, because it's a general construction, you're going to sometimes obfuscate non-null programs and so on.
Right, exactly.
Talk about the technique, kind of, how to use it in applications.
I see. Good. Right. So again, right. So if you know it's null program, then you don't do anything. So we get around that by requiring that correctness holds even for non-null programs. So I don't.
The rest be how to use it, right?
Yeah. So I don't have general applications for null except for, let's say, witness encryption. Maybe Daniel will have other applications. But I just want to say that, as again I mentioned earlier, even having proof techniques for now, or the proof techniques themselves, gives us a lot of insight into
I guess
applications beyond just.
I guess one general paradigm could be if you can design two programs where one is a null program, the other one is computationally indistinguishable to a null program, then you can use null program security. So start with the program P that is not null, but is computationally indistinguishable to a null program.
Like this humming thing, right? Maybe like Yuval's thing, the fuzzy humming ball or something like that, right?
If you
That's not give it if you use, right? I mean, does it give us something obviously usable directly? Like you get obfuscation for null program, let's now obfuscate Yuval's thing, the fuzzy ball. What can we say? What can we conclude from this so it's unclear?
Yeah, so I don't know. But going back to Richard's question, I'm not sure if that completely works. For instance, I don't know how to prove security of the GGH15 construction for evasive programs. So these are programs that potentially could have accepting inputs, but for which it's computationally hard to find accepting inputs. For this program, I actually don't know how to prove security of these things from evasive outer
Because my point was just that Evgeny was asking a general template of using null obfuscation. And general template would be to design programs that are computationally indistinguishable and then use null obfuscation security.
True.
So that just the hybrids are kind of like spread out.
Yeah. I'm just saying that the one has to be a bit careful about doing the hybrid. Because sort of a program that is computationally null, so for which you cannot find accepting inputs, a priori may seem like computational indistinguishable from a null program. But
for instance, when you try to prove predicate hiding security for attribute-based encryption using lockable obfuscation, you start with a program that has an accepting input, but you change it to kind of like a always rejecting program, and at that point you can check its security.
I see.
That is template. I'm trying to sort of mirror the template. I'm not saying that always will work, but that has to be. I mean, it's been known to be a template that has worked in the past.
Hoeteck? Sorry. Is this fix in the bottom enough for VW or like the aux thing?
Yeah.
Is that enough for VW? To like show.
Yes. Because the good. That's a great question. Yes, because when you apply the assumption, you are going to apply to some intermediate A's. And this thing splits into two parts. And the point here is that the S's here are independent of the S's here. All right. So in fact, that's a great point. So the question is whether this version is sufficient for our security proof. So one interesting point is that our security proof works even if the S matrices are not independent. So all the SI zeros are some S0, and all the SI1s are some S1. Our security proof still works because the BMR proof still works if you reuse the S matrices. But if you use this version of the assumption, then you have to make sure the S matrices are independent. Otherwise, the proof doesn't go through anymore. And it so happened that the original construction chooses the S matrices to be independent. So, right now, it's not clear if you make the S's the same, whether there's actually an attack on the scheme. And so your attack in sometimes suggests that maybe if you make the S's the same, there is an attack on the scheme.
If they're independent, does that mean Oxs is just empty? Is Oxs empty in the
Is Ox-S empty?
the construction?
The Ox-S is sort of the S's themselves. So the Ox-S is S itself. That's all. So the Ox-S is basically public coin. Yeah, so when you apply the assumption, the Ox-S will be the S's that on some particular A that you apply the assumption on is the S's that go before the A's, and the P's will be the S's that go after the A's.